I am Tejasvi. I am working as assistant professor in physics in Mallareddy Engineering College for Women. In this video, I am going to explain about fiber optics, and the contents under this topic is the introduction of fiber optic materials, the principle used in the fiber optics, and acceptance angle, acceptance cone, and numerical aperture, types of fiber optics, losses of fiber optics, and how communication takes place in these fiber optic materials and applications. So what is an optical fiber? This is the material used for communication purpose. Instead of using copper wire, like in copper wire, electrons carry a message like in the form of electricity from one end to another end. Whereas in optical fiber, the message is carried from one end to another end in the form of light. Okay, this is more useful than the ordinary copper wires. So how the light energy move from through these materials? What is the principle used? Okay, the principle is total internal reflection. So what is total internal reflection? When a light ray passing from denser medium to rarer medium, the ray refracts in the rarer medium. So here this is the incident ray and this is the refracted ray. The angle of incidence, here it is the angle between incident ray and normal, and angle of refraction, it is the angle between normal and the refracted. As the ray is moving from denser medium to rarer medium, in rarer medium the velocity increases, hence it moves away from the normal. So the angle of incidence is less than the angle of refraction here. So if the angle of incidence is increased in denser medium, so what happens? The ray bends still away from the normal, and hence there is an increment in the angle of refraction. Still, if the angle of incidence is increased further, at a particular angle of incidence, the ray, that is the refracted ray, grazes the surface of the medium. So that particular angle of incidence is called critical angle. So what is critical angle here? When a light ray moving from denser medium to rarer medium at the angle of incidence where it is equal to critical angle, the refracted ray grazes the surface of the medium. It moves along the surface of the medium. That is, here angle of refraction is 90 degrees. So when angle of incidence is equal to critical angle, the angle of refraction is 90 degrees. So at this case, how these refractive indices related to critical angle is, so let N1 be the refractive index of denser medium, N2 be the refractive index of rarer medium. Then from Snell's law, sin I by sin R is equal to N2 by N1. So sin I is the angle of incidence, that is theta C. Sin R is here angle of refraction, that is 90 degrees. So sin 90 is 1. So sin theta C is equal to N2 by N1. This is the relation between critical angle and refractive indices. Okay, now still if the angle of incidence is increased beyond this critical angle, then the ray reflects back into the same denser medium. This phenomenon is called total internal reflection. So what is total internal reflection now? When a light ray is moving from denser medium to rarer medium, the ray reflects back into the same denser medium when angle of incidence is greater than the critical angle. This phenomenon is called total internal reflection. Okay, using this principle, the rays are moving in the optical fiber material. So what this optical fiber material consists of? These are the long wires containing high refractive index material at the center, that is called core. So this is the core material, and this core is surrounded with another optical active medium, that is cladding, which is less refractive index than core material, such that total internal reflection condition satisfies in the core material. Here we have to remember that light passes through the core material. So the light rays, as it should not escape from this core material, cladding material of less refractive index is surrounded on this core material, such that the rays takes total internal reflection in the core material. So generally this core has the diameter of 5 micrometers to 100 micrometers, and cladding material, it is surrounded, its thickness is very small. To protect these two layers, some insulating materials are used, like coating or strength membrane or outer jacket. Like here, three membranes are shown. Some wires will have only single membrane or some two. Okay, depending on the material of core and cladding, this outer covering is arranged. This outer covering thickness generally varies from 250 to 300 micrometer in diameter. Okay, this is the structure of the optical fiber. It consists of core at the center, through which the light rays pass through them, and cladding is surrounded to this core material, which is having less refractive index than core. Now, the rays should enter into this core material such that in this at this core cladding interface, the angle of incidence should be greater than the critical angle, so that total internal reflection takes place. So to make this total internal reflection in this core material, the launching angle into this core material is important here. So for this, let us measure this launching angle. So for this, let NO be the refractive index of the medium outside this core material. Let it be air. So let NO be the refractive index of the medium here, and N1 be the refractive index of the core material, N2 be the refractive index of the cladding material. I is the angle of incidence at air to core material, and R is the angle of refraction at air core medium, and here this is the angle. So now later, so here the light rays that are entering from the outer medium into the core material. So here refraction is taking place, like the light ray is entering from rarer medium to denser medium. So applying Snell's law at air core interface. So Snell's law is sin I by sin R is equal to like N2 by N1. That's the general formula. So the refractive index of the second medium, here it is core. So it is taken as N1. So N1 by refractive index of the first medium is NO. So sin I by sin R is equal to N1 by NO. So sin I is equal to N1 by NO into sin R. Okay, now let us take the like this triangle. So here this is this angle is angle of refraction, and here let it is taken as theta, and this is as this angle is 90 degrees. So here it is forming a right angle triangle. So name it, and let us take like this figure has modified, like let this triangle is ABC. Here at angle A is R, and at B angle that is theta, and C that angle is 90 degrees. So from triangle property, R plus theta plus 90 is equal to 180. So R is equal to 90 minus theta. Now taking sine on both sides. So sine R is equal to sine 90 minus theta, that is equal to cos theta. So sin R we got as a cos theta. So substituting that sin R in the previous equation, we'll get sin I is equal to N1 by NO into cos theta. This is one relation we got. Here theta is angle of incidence at core cladding interface. So if this angle is a critical angle, then that is the maximum angle that it is entering at air core interface. So I maximum, so this is the acceptance angle. So where the angle of incidence at core cladding will become critical angle. So at critical angle, I becomes I maximum. So sin I maximum is equal to n1 by n0 into cos theta c. Now taking a trigonometric relation as cos theta c is equal to root of 1 minus sin square theta c. So sin theta c, where theta c is the critical angle. So sin c, there we have seen a near total internal reflection. So critical angle theta c, sin theta c is equal to n2 by n1. Substituting here, we'll get cos theta c is equal to root of 1 minus n2 square by n1 square. Taking LCM, we'll get cos theta c is equal to root of n1 square minus n2 square by n1 square. That equal to root of n1 square minus n2 square by this n1 square is brought out of the root, it will become n1. So we got cos theta c. Substituting this cos theta c here in the sin I maximum formula. So sin I maximum is equal to n1 by n0 into root of n1 square minus n2 square by n1. So sin I maximum is equal to root of n1 square minus n2 square by n0. Therefore, I maximum is equal to sin inverse of root of n1 square minus n2 square by n0. So this is the maximum angle beyond which this here the total internal reflection, that condition fails. So that this is the maximum angle of incidence, and less than this angle all these rays will satisfy the condition of total internal reflection in the core material. So this maximum angle is called acceptance angle, and this angle, if it is taken in 360 degrees around this normal, that is axis of the core, so it becomes like a cone. So that cone is called acceptance cone. So the light rays which are entering through this cone, they propagate through this core material, which is necessary for communication through light rays. Okay, numerical aperture. This also gives the condition for the light rays to enter into the core material. So what is numerical aperture? It is nothing but sin I maximum. Sin I maximum is shortly defined as numerical aperture. It gives the ability of an optical fiber to collect the incident rays that are that are entering inside it. So now consider a fractional difference in refractive indices. That is fractional difference, right? So that means n1 minus n2 by n1, that is given as delta. So this is the fractional difference. Now let us take, because sin I maximum is having root of n1 square minus n2 square. So for that, let us take n1 square minus n2 square by n1 square. n1 plus n2 into n1 minus n2 by n1 square. Though the refractive index of cladding is small than the refractive index of core material, but the difference is very, very small. So almost in this addition, we can take n1 is equal to n2. So this will become 2n1 into n1 minus n2 by n1 square. Here this n1 gets cancelled, it will become 2 into n1 minus n2 by n1, that equal to 2 delta. So finally we'll get n1 square minus n2 square is equal to, this n1 square comes to the right hand side, so a 2 n1 square delta. So substituting this n1 square minus n2 square value in the sin I maximum value. So the formula will get Na is equal to sin I maximum is equal to root of n1 square minus n2 square by n0. So that root of n1 square minus n2 square is 2n1 square delta. So n1 is coming out. So root 2 delta by n0. So this is the formula for numerical aperture, or simply sin I maximum. For air, the refractive index is 1. So substituting that NO is equal to 1, we'll get Na is equal to N1 root 2 delta. So this from this formula we can also measure numerical aperture. So more the numerical aperture value, the better the optical fiber. So we have to choose the optical fiber materials such that it is having high numerical aperture values. The types of optical fibers. Basing on different categories, these optical fibers are classified as The first category is depending on the material used. So glass fibers, if the core and cladding are made of glass material, so they are called glass fibers. And plastic fibers, if they are made with plastic material. Then the second category is depending on number of modes. What is mode here? Mode means, say as we have seen earlier, the light rays that are entering the core material in the acceptance cone. So within that acceptance cone, with any direction it can enter. Means it is the light ray is having different angles of incidence. So different angles of incidence will have different uh, path it will take. So these paths, the rays that are taking are called modes. So basing on modes, these optical fibers are classified into two types: single mode fibers and multi-mode fibers. Single mode fiber means only one single path they'll take, the rays will take. This is possible only when the core is having small diameter, that is 2 to 8 micrometers. So if the diameter is very small, so only one or some very slight single mode is possible. So if the diameter is large, that is nearly 50 micrometers, then different modes will propagate through these fiber optic materials. So this is called multi-mode fiber. Okay, so basing on number of modes, there are two types of optical fibers: single mode fiber, which is having small diameter 2 to 8 micrometers; multi-mode fibers, which is having larger diameter 50 micrometers. Then on the third category is depending on refractive index profile. So that is, first one is step index fiber and the second one is graded index fiber. So step index fiber means here the refractive index of the between the core and cladding will change like a step. Means the refractive index of this core is completely uniform and refractive index of cladding is uniform and lower than the core material. So it changes like a step. So one time change will be is observed in this step index fiber. So in this step index fiber, if the core is having small diameter, only single mode transmission is seen. If the diameter is larger, that is nearly 50 micrometers, then multi-mode transmission will take place. See, when multi-mode transmission is taking place means at the other end, we can see like, see this center line, the rays which are passing along the axis, they travel the smaller distance. So they reach the other end first. Whereas the rays which are taking more number of reflections, see here, this is taking more number of reflections. This will take more time to reach the other end. Means all the modes are not reaching the other end at the same time. So this is a drawback. So the signal will is getting distorted here. To avoid this drawback in multimode transmission, graded index fibers are designed such that here the core material itself will have gradual decrement in the refractive index. So there is no stepwise decrement between core and cladding. There will be a gradual decrement in the refractive index starting from the center of the core moving to the cladding side. So when this gradual decrement takes place, what happens is, see the ray which is passing along the center of the axis, it is traveling in the high refractive index material. So as the refractive index is more, velocity decreases. So it takes more time to reach the other end. So the rays which are taking, like here also, here as the refractive index is decreasing, so wherever the total internal reflection condition is satisfying, there the reflections takes place. So, so wherever it is possible, the rays are taking their own directions and they move. So as the rays which are taking longer path, they are moving in less refractive index material. So as they are moving in less refractive index, their velocity is more. So as here velocity is more, they reach some less time to reach the other end. So though the modes they are taking different paths, because of change in the velocities, almost nearly, not all we can say, nearly maximum number of rays will reach the other at same time. So the disturbance is decreased in this graded index fiber materials, that is in multimode transmission. So how this gradual decrement takes place? It takes according to a formula. N of R is equal to N1 into 1 minus 2 delta R by A power alpha 1 by 2, where N1 is the refractive index of core, that is at the center. Delta is the fractional difference of refractive indices. R is the distance from the core. So from the center of this core, where we want the refractive index, there at that place, that distance is R. A is the radius of the core material. So this here from center to here, this is the radius A. Alpha is the graded profile of refractive index of core material. This is for a particular optical fiber, this alpha is constant. So by satisfying this condition, there will be gradual decrement in the refractive index in the core materials, that is between 0 to A. 0 to A means in the core material. So if it is a cladding material, that refractive index is equal to N1 into 1 minus 2 delta power 1 by 2. So this if this is expanded using exponents, this will become n1 into 1 minus delta, where delta is n1 minus n2 by n1. Subtracting this will get that is equal to n2. So this cladding material is having a refractive index of n2. So now let's see the differences between step index and graded index fibers in detail. So in step index of fiber, the refractive index is uniform throughout the core and the cladding material. There will be a decrement of refractive index sharply as a step. But whereas in graded index fiber, at the center axis of the core, refractive index is maximum, and from center, if we are going to the ends, the refractive index decreases gradually. In this step index fiber, there is a chance of single mode and multi-mode, but whereas in graded index fiber, only multi-mode transmission will take place. Like refractive index, here in this core material, it is equal to N1, that is R less than A means that is the core material. R greater than A, it is cladding material, the refractive index is N2. But whereas in graded index of fiber, in core material, the refractive index varies as N1 into 1 minus 2 delta R by A power alpha power half. Whereas in the cladding material, that is equal to N2. Signal distortion, this in this step index fiber, single mode transmission, there is no there is very like we can, there is no signal distortion. But whereas in multi-mode transmission, there is a high signal distortion is observed, but that distortion is decreased in this graded index of fiber, that is in multi-mode transmission. This graded index of fiber is more advantageous. Light rays, they pass as a zigzag manner in this step index fiber, whereas in graded index fiber, they take a helical path or a skew rays. They move like in a skew rays type. The bandwidth is lower in step index and it is higher in a graded index fiber. Diameter is around 50 to 200 for a multimode transmission and nearly 10 micrometers for single mode transmission. Whereas in graded index fiber, the diameter is about 50 micrometer. Applications, this step index fiber is used in short distance communication, and this graded index fiber is used in long distance communication. Then attenuation. Attenuation means losses. Loss in the output is more in multimode transmission through step index fiber. So these losses are less in the graded index fiber. The cost of this is step index fiber is less expensive, means just synthesizing the core material and fitting the cladding is enough. But whereas graded index fiber, it is highly expensive, that is synthesis itself takes a high cost, because the refractive index should change gradually. If there is any manufacturing defect, then the rays will escape out in the cladding material, not satisfying the condition of total internal reflection. So it's a very high care should take in the synthesis of this graded index fiber. In numerical aperture for multimode transmission it is high, whereas in single mode transmission it is less. This graded index fiber numerical aperture is less. Pulse broadening is present in this step index fiber. This here no pulse broadening is observed in this graded index fiber. Okay, these are the differences between step index and graded index fiber. So graded index fiber is more advantageous than step index fiber. Okay, now the losses of optical fibers. The always we can't expect 100% output. Any work there will be having some losses. These losses in the output is called here attenuation. So attenuation means the loss in the output when compared to inputs. Attenuation is measured in decibel per kilometer and it is given by the formula 10 into log input intensity by output intensity base 10. So the losses in these optical fibers is observed like some absorption losses, scattering losses or bending losses. So let's see one by one in detail. So the first loss is scattering loss. When there are some any defects in the manufacturing of this material in the core, or if there are any impurities present in it, where these impurities the light scatters and hence the intensity decreases. There that light ray, that intensity decreases, so that it is not reaching the other end, hence the intensity, the output intensity decreases. So this type of losses are called scattering losses. This occurs due to the presence of impurities, that is dopants, in this core material. This is eliminated by taking proper care during the synthesis. Okay, next loss is absorption losses. Some rays are like ultraviolet absorption, infrared absorption, ion resonance absorption are observed. So some type of molecules or atoms, they absorb the radiation. So here we can say ultraviolet absorption, and these OH minus ions, they are absorbing the radiation and infrared absorptions takes place. So these absorptions, these can be avoided taking like depending on the material. So if the material is containing like water molecules, water means it contains OH minus ions like iron, copper, chromium. These are the ferromagnetic substances. So these are absorbed basing on the materials that is used for this in this fiber optic materials. So some materials they absorb different types like ultraviolet, some are absorbing infrared. So basing on that suitable wavelength of the radiation is selected for reducing the absorption losses. Then third loss is bending loss. When the wire is bent, so there will be, when the wire is passing means surely there will be bends in it. If that bend is beyond a certain limit, then total internal reflection won't satisfy. So that limit is called the radius, and that loss is given by the coefficient alpha b is equal to c into exponential minus r by rc, where c is some constant, r is the radius of the curvature of the bend. Here how to what extent it is bending, so that radius of curvature, and rc is equal to a by na square, where a is the radius of the fiber, that is core material, na is the numerical aperture. So within this limit, within certain limit, that bending is permissible in these optical fiber materials. So again, this bending we can observe in two types: micro bending losses and macro bending losses. Micro bending losses means when there is heavy weight or some pressure on this, the wire will be having some bend. So that is called micro bending. Macro bending means the bending of the wire at wherever it is necessary. That is called macro bending losses. This is avoided by taking a condition to what extent it can be bent. So that radius r should be measured. So basing on that only the wire should bend. Okay, then fourth losses are losses due to dispersion. So the light rays when it is passing through this material, the rays, it can the pulse width may increase, the amplitude may increase, or the spacing between these pulses may increase. So this decreases the output intensity. So these type of losses are called dispersion losses. Dispersion losses again are classified into two types: intermodal and intramodal. Intermodal dispersion is the pulse broadening takes place due to the delay in the different modes passing through this material, that is a multimode fiber materials. Whereas intramodal is the pulse broadening is taking place due to the refractive index of the material used. So these are the four types of losses we have seen, that is scattering losses, absorption losses, bending losses, and losses due to dispersion. These losses almost they can be minimized, but nothing can be avoided completely. So by taking proper care, like choosing particular wavelength of the light for communication and avoiding the manufacturing defects, these losses can be minimized. Okay, now let's see how the communication takes place through these optical fiber materials. So that is called optical fiber communication system. So in any communication system, there will be some transmitting station and receiver station. So here also transmitter will be there and receiver will be there, and the communication takes place. The transmission path here used is optical fiber. So this is the wire that is taking the message from the transmitter to receiver. So here the light rays are used for communication. So in the transmitting station, that light rays are modulated here. So let's see how it will take place. So in the transmitter there will be three parts, that is input signal, that what should be sent to other place, that is the input signal, and optical source is used. So this optical source is modulated with the input signal. Like here, this optical source is the carrier, it is carrying the message. So these two are merged at this modulation. This is called modulation. By putting that one wave into another wave, that is called modulation here. That is done here at modulator. So once it is got modulated, the light rays passes through this transmission path, and their optical detectors or photo detectors are placed to identify the light rays. So once it detects the optical rays, that it detects, so once the photon is coming, it is converted into, so this electrical energy then it is carried to demodulator, which separates the output signal here. So that output signal went to the wherever it is necessary. So this is the process that is taking place. Okay, so here in this, the transmission path, in this transmission path, the type of material used is optical fiber. So what are the requirements of good light source at transmitter? That main condition is it should emit monochromatic light. Okay, generally laser lights are used as it emits a single wavelength. The emission bandwidth must be as small as possible, and these light rays that is coming from this source, it should travel longer distance without any attenuation. And this light source must be suitable for modulation techniques. This light source must be small and efficient. It should be long durable, and should not be expensive. It should be less expensive. Generally LEDs and laser diodes are used as light sources. Then modulation, how this optical modulation takes place. If LEDs and diode lasers are used, the modulation is achieved by them directly. So in this semiconductor diode lasers or LEDs, no such external modulators are necessary. Directly, these can be directly modulated, but that is called as internal modulation. But if laser light is used, like gas lasers or solid state lasers, here direct modulation can't take place. So external light modulation is needed. So that modulation is like analog modulation, which varies analog modulation, in which amplitude is continuously modulated with respect to time. and pulse width modulation. Here the signal it is here the signal is continuously modulated with the pulse. And binary digital modulation, the signal is sampled at regular intervals. So binary means here only two digits will be using. 0 indicates the absence and 1 indicates the presence. So this is about the modulation, and once the light rays are passing through this material, it moves to the receiving station. There it goes to the photodetector. Photodetectors, the main characteristics of this is a high photon to electric current conversion efficiency should be present, and it must be able to operate at high frequencies equal to the frequency of modulation, and low reverse current or dark current in the absence of signal. Low signal dependent noise, pin diodes and APDs, avalanche photodiodes, are mainly used for this purpose. The converted signal is now amplified, demodulated, and finally output is obtained. So this is how the communication taking place in this optical fiber materials. Okay, where these optical fibers are used nowadays in these are having a vast applications. That firstly in medicine. So in medicine, to see the invisible body parts like stomach or kidneys, to know the foreign parts in these body parts, the material, these optical fiber wires are sent through a small hole in the body, and and the other end is connected to a system. So the light rays, they enter into this optical fiber, and they so the light rays, they reach over there. So using these optical fibers, the internal body parts are visible, are seen, and then they are used for the cuttings, lasers for surgeries, gastroscope, orthoscope, endoscope, etc. And in defense, these are used as hydrophones for seismic waves and sonar. And data storage devices, these optical fibers are used. And telecommunications also, they are used, like net in networking purpose. Like in industries, these are used in producing high temperatures and high pressure. In broadcasting TV, that is in communication, these optical fibers are used. And in sensors, in displacement sensor or fluid level detectors, liquid level detectors like temperature, pressure sensors, these optical fiber materials are used. Okay, this is how the communication is taking place in the military. So near a transmitting station, from there a wire is coming to a receiving station. So the messages, they are sent through these fiber materials is safe than the ordinary telephone messages. Okay, thank you.